Good afternoon, everyone. We are going to start the week 6 live sessions and we'll be starting in 5 minutes. So I'm going to share the screen. So I hope the screen is visible. So the first question is, what is the difference between mixing and blending? What is the difference between mixing and blending? What is the difference between mixing and blending? So mixing and blending are almost same. They are used interchangeably. Okay, so if I write, mixing is a process that tends to result in randomization of dissimilar particles. Okay, it mixes different size. Mixing is a process where it mixes different size of dissimilar particles. Okay, and blending is to smooth to mix smoothly and inseparably together during which a minimum energy is imparted. So both of the process are for homogenization between two different size of particles, maybe one solid on one liquid particle, maybe two liquid fluids, or maybe some gas and solid particles also can be there. So any kind of thing in two phases are coming together and creates a homogenized mixture, that is done by mixing or blending. Okay. So from the video also you can understand. So I hope my screen is visible, right? So you can see here the solid feed is different type of two solids are feeded, and they are mixed, right? This is also you can see a mixing or blending, right? This is a mixing between two fluids. Okay. Second, what is the difference between mixing and agitation? Now we have still learned that mixing and blending are same, but not mixing and agitation are same. So what is agitation? It refers to the induced motion of a material in a specific pattern. Okay. So in case of agitation, what happens? In a specific pattern, particles or fluids are mixed. But in case of mixing, it is a rather a random distribution. Okay. So here also you can see a video. This is a bottom bed. This is a valve in the agitator, discharge, and motor, gearbox, and mechanical. These are the different parts of the agitator. So feed is given inside the chamber, and now you have see the induced motion is created through these blades of the through the blade of the starter, right? That is why in some kind of external force is there to create the mixing. That is why it is called agitation. It is also one type of mixing, right? So different types of samples are coming and it is agitated. So in drying also agitator can be used. In washing also agitator can be used. In cooling also you can see in cooling also agitator can be used. Okay. Now, which method is used for making capsules? Which method, which mixing method is used to make capsules? Which mixing method is used for making capsules? What is that? The answer is wet mixing, right? So the answer is wet mixing. Wet mixing is generally considered in the granulation step in the production of tablets and capsules. So there are different type of mixing, right? So one is wet mixing, second one is dry mixing, and third one is dry blending. All are almost same, okay? But they are used for different purposes. They are dependent on the material we are using and use. So dry mixing is done for several ingredients ready for direct compression as in tablets, and dry blending is suitable for powders in capsules. Okay, so dry mixing is for the solid bigger size particles and dry blending is for the powder samples, dry syrups, etc. So we'll see the videos. So you can see the wet mixing plant. These are to the vibrators, removable bunker body extensions for transportation in container. So these are different parts. Feeding bunker, from here feed will be happened. So this is how you see. These are the nozzles, spraying nozzles from where cold or wet water will be coming, right? Now see. So different type of particles are going. Now water dosing will be happen. There is a pump which controls the water pressure. Now see, water losing is happening. Now cement is going, cement dosing. So cement is mixing. Cement is also a liquid type of thing, right? Next is emulsion dosing. It is emulsion means also the colloidal particles, and there is dispersed phase and there is continuous phase. So it is also going there. Again cement dosing happened. Right? So this is how wet mixing plant works. Next one is the dry mixer. This is the different parts of the system. And now, so this is the fine particles. Mixing is happening. So this is the dry particles are mixed. Now heating is happening. Now from the bottom discharge is there, right? So this is the dry mixer. Now we'll see the dry blender. So you can see from both sides two materials are coming, and this is a V-shaped blender which is rotating along axis, and the particles are mixed. Right? So these are the three types of mixing methods. Next, compression method is used in which method? So the answer is dry mixing. What are the different types of mixing? What are the different types of mixing? first one is the convective mixing. Second one is the diffusion mixing. And the third one is the shear mixing. So convective mixing means the groups of particles are moved from one position with a pattern, mixing two or more groups of solid particles so that they are dispersed in each other. Diffusion mixing means the particles are distributed over a freshly developed interface. The powdered materials are mixed in a container where the movement of the powdered particles occurs by tilting the material beyond the angle of repose. And shear mixing is the momentum exchange of powder particles having different velocities leads to shear mixing. So shear mixing is happening due to the shear stress or shear force. Okay, and diffusion mixing is more among the powdered materials, and convective mixing is for the larger particles. So shear mixing can improve semi-microscopic mixing and be favorable in both batch and continuous process. However, they are different, but when during a powder mixing, all the above three mechanisms take place together. All this convective mixing, diffusion mixing, and shear mixing. Next question is, what is angle of repose? We will show the videos, but before that, I'll repeat I'll make you understand what is angle of repose. So, angle of repose is a rapid method of assessing the behavior of a particulate mass is to measure, like this measurement is called the angle of repose. Now, if solid is poured from a nozzle onto a plane surface, it will form an approximately conical heap, and the angle between the sloping side of the cone and the horizontal is the angle of repose. So suppose there is a plane surface and you are pouring like salt, maybe salt or powder. So when you pour, you will notice, you maybe have noticed that it forms a triangular heap kind of thing. And this angle between the horizontal and the slant height is called the angle of repose, right? So it will be clear from the videos. So we'll see this. So you are seeing that there is a nozzle and heap of powder or salt is forming, and it is creating a sharp kind of heap. And now if you see this, if you notice my cursor, you will see that this slant angle and this is the horizontal angle, horizontal plane. The angle between these two is called the angle of repose. So it is angle of repose taster, right? So it is the steepest angle of descent relative to a horizontal plane. Powder is poured to create an angle from 0° to 90°. So initially, when very less amount of powder is there, it is just a 0°. And now we are increasing the amount, and now it is showing the 48° angle of repose, right? It is showing the 48° angle of repose in this case. Now, if still we again increase, it will increase the angle from 48 to 90. It is the previous one was irregular shape. This is the regular shape, and this is the different kind of heap they are creating with this taster. So this is just showing the taster. Next question. Gravity in bed mixing device is an example of active mixer. Is it true or false? Gravity in bed mixing device is an example of active mixer. So, uh, now gravity in bed mixing is an example of active mixer or not? Gravity in bed mixing is an example of active mixer or not? The answer is not true, false. So gravity in bed is a passive mixer. Passive mixer. So what is passive mixer? It is in this system randomization of the materials is achieved by directed flow of the powder streams by baffles, etc. And another mixer is active mixers. The active mixers uses certain moving parts to assist in the randomization of the solid materials, or the mixer machine moves about physically in this mixing process. Okay. So active, in case of active mixing, the direct involvement of the material or direct involvement of the machine is required. Next question. Dense powder and abrasive materials are mixed in which blender? Dense powder and abrasive materials are mixed in which blender? The answer is tumbling. The answer is tumbling type of blenders, where dense powder and abrasive materials are mixed. Next, what is the purpose of ribbon blender? What is the purpose of ribbon blender? So in ribbon blender, materials ranging from low density, finely divided materials that aerate rapidly to fibrous or sticky materials that require positive discharge. It can be blended in this ribbon blender. Can be blended in ribbon blender. A broad ribbon can be used for lifting as well as for conveying, while a narrow one will cut through the material while conveying. Okay, so these are the purpose of using ribbon blender. Next question. What is the name of the blender that uses a conical vessel and reduced power consumption? What is the name of the blender that uses a conical vessel and reduced power consumption? The answer is vertical orbiting screw blender. The vertical orbiting screw blender batch type consists of a conical vessel with a rotating screw which lifts powder from the base of the conical vessel to the powder surface, while at the same time orbiting around the vessel. An advantage of the orbiting screw design is that mixing is rapid here and the power consumption to produce a uniform blend is thus considerably reduced. Okay. So this is your vertical orbiting screw blender. Next question. What are the large rotating wheels and a set of scrapers are called in Muller mixers? What are the large rotating wheels and a set of scrapers are called in Muller mixer? The answer is Muller turret. So that's large rotating wheels and a set of scrapers are called Muller turret in Muller mixers. Next. Muller mixers are used to mix solids with liquids to produce paste. Is it true or false? Muller mixers are used to mix solids with liquids to produce paste. It is true or false? Muller mixers are used to mix solids with liquids to produce paste. Is it true or false? The answer is true. Muller mixer produces paste. Next, what is used to improve the cross flow of solids in drum type blenders? What is used to improve cross flow of solids in drum type blenders? The answer is internal baffles or helical plates. So, in case of drum type blenders, there are internal baffles and helical plates to improve the cross flow of solids inside the blender. Next question. Talk about the different types of blenders. Talk about the different types of blenders. So talk about the different types of blenders, right? So till now we have learned there are so many blenders, right? Batch type blenders, continuous type blenders. So we'll learn we'll see the videos one by one. So first one is the twin shell blender or V-type blender or tumbling blender. It can also be called tumbling blender. So you can see how they are mixing, right? So again, if you see that this is the mixing type. This is the mixing type. Okay. Next is the ribbon blender. So this is the different types of ribbon blender. Different types parts of ribbon blender. This is the end bearings, flush discharge valve. Technical features of this are stainless steel, grit silking mirror polishing, heavy duty mixing chamber. So now we will see. This is the ribbon blender. So two types of fluids, solid particles are coming and they are mixed with this blend. Okay. Next is the vertical screw mixer. Okay. The vertical screw mixer. So this is a real example. You see that two screw type of blenders mixing are there in a vertical surface. Okay. Next, so it is the Muller mixer, continuous Muller mixer. So you can see. So it is written that the wheels compress materials against the pan bottom while the scrapers move the material from the pan sides and center to flow under the wheels. Okay. So this is the typical Muller mixer. So that is how they are separated. Next one is the single rotor blender, single shaft rotor blender. They are mixing to their different types of blades are used. You can see, right? Standard tooth edged blade type tooth blade. Okay, so blade type shovel tools are used for mixing. So different types of blades are used. So you can see how they are mixed. single shaft rotor blender. Hmm. Next one. Next one is the continuous mixer. Next, now till now we have learnt about the batch mixer. Now is the continuous mixer. So you can see in the continuous process, feeds are coming, they are mixed, feeds are coming, two different types of feeds are coming, they are mixed along the way and they are separated, right? This is the continuous mixing. Next one is about the pug mill. The pug mill consists of a drum or trough-shaped vessel equipped with a double-shafted or less often single-shafted agitator. Okay. The paddles are usually adjustable. So you can see the paddles here. So these are the paddles, right? Paddles are usually adjustable so that their forward and backward motion can be varied during mixing. So this is a pug mill. Next is static mixer. Next is static mixer. You can see that flow is coming and without any movement due to the baffle, the fluid is mixed. So static mixing is also called the motionless mixer, which consists of a cylindrical chamber in which chaos induce inducting element. So here the chaos inducting element was this baffle, right? So that helps in mixing of the liquids. Next is the zigzag rotor. Next is the zigzag rotor. Okay, so this is the zigzag rotor. Last one is the kneader. Kneader. So this is the mechanic part. So you can see how shaft is also moving and having an oscillating motion, right? This is the melting zone and particles are mixed. These are some fillers are mixed. So how you can see how it is a continuous process. So along the way, everything is happening from coming feed to mixing and processing and finally the outlet. Right? So this is the kneader. This is the whole kneading technology or kneader technology. Okay. Next question. Mixing time is short in case of batch blenders. Is it true or false? Mixing time is short in case of batch blenders. Is it true or false? The answer is false. Because in case of continuous blenders, in case of continuous blenders, mixing time is less. Next, standard deviation diminishes to zero as mixing proceeds. Standard deviation diminishes to zero as mixing proceeds. Is it true or false? Standard standard deviation standard deviation diminishes to zero as mixing proceeds. So the expression of standard deviation you know, right? So S is root under summation of xi minus x whole square, where I is 1 to n, divided by n minus 1, right? So n is the total number of samples, xi is the volume fraction of each of the tracer, and x bar is the average volume percentage. Now the answer is true. So as mixing proceeds, all kind of particles are distributed in almost similar size or average size. All kind of particles achieve almost an average size. So standard deviation becomes 0. Next, low value of standard deviation means bad mixing. Low value of standard deviation means bad mixing. Is it true or false? Low value of standard deviation means bad mixing. It is false. Because if the standard deviation value, just now we have seen that if the standard deviation value is diminishing, that means it is created a almost homogenized mixture. So low value of standard deviation means good mixing. That is why it is false. It will lead to good mixing. Next, what is the zero mixing condition? What is the zero mixing condition? What is the zero mixing condition? Zero mixing means before mixing has begun, the material in the mixture exists as two layers, one of which contains no tracer and one of which contains all tracers. This condition is called zero mixing. And here sigma 0 is called the zero mixing condition. It is root under mu into 1 minus mu. And mu is the overall average fraction of tracer in the mixture. Okay, so this is the zero mixing condition. Next, in batch mixing, what is the value of mixing index at the start? In batch mixing, what is the value of mixing index at the start? In batch mixing, what is the value of mixing index at the start? The answer is unity. Mixing index is unity in case of batch mixing at the initial condition. Next, higher the value of mixing index, the dash is higher. Fill in the blanks. Higher the value of mixing index, higher the value of what? So what is mixing index? Mixing index is defined as IP into sigma 0 by S. Now if we write the expression, it will be n minus 1 mu 1 minus mu divided by summation of xi minus x bar whole square I equals to 1 to n. So this is the mixing index, right? Mixing index is high means the mixing is also high. The quality of mixing is also high. Okay. Next question. The mixing index would become infinite at long mixing time. Is it true or false? The mixing index would become infinite at long mixing time. The answer is true, right? True. Next. Mixing rate is proportional to driving force. Is it true or false? Mixing rate is proportional to driving force. Is it true or false? The answer is true. Mixing rate is proportional to its driving force. Next, what is the Lasse mixing index? What is the Lasse mixing index? So the expression of Lasse mixing index is Sigma 0 square is the mixing index, right? This is S is the standard deviation square. Sigma 0 square minus sigma r square. So all other expressions you know already. Sigma r square is mu into 1 minus mu by n. Okay. N is the average number of particles in each spot sample. Okay. So Lasse mixing index is 0, IL is 0. It would represent complete segregation. Complete segregation. That means particles are separated, not started mixing. And a value of unity, so IL is 1, means completely random mixture. Completely random mixture. Okay. Practical values of Lasse mixing index lies between 0.75 to 1. Okay. This is the expression of Lasse mixing index. Next, what is slurry? What is slurry? So what is slurry? What is slurry? Slurry is the mixing of fluids with other miscible or immiscible liquids, gas, and with fine particles. So this is the slurry. This is a mixture of all the things. Next question. Different methods of slurry mixing. Talk about the different methods of slurry mixing. So, first one is the turbulent mixing. It is the highly effective mixing due to turbulent flow, which results in random fluctuation of the fluid velocity at any given point within the system. And fluid velocity at a given point change in three directions, that is x, y, z. Second one is the laminar mixing. So turbulent one is the irregular mixing. Laminar one is the regular mixing. So here two dissimilar liquids through laminar flow, that is applied shear stretches the interface between them, suitable for liquids which require moderate mixing. And the last one is the molecular diffusion. It is the mixing at the molecular level. So we'll see the videos and it will be much more clear. Yeah. So this is the turbulent mixing. You can see that how vigorously it is mixing and it doesn't have any particular direction of mixing. And it can mix in any direction, X, Y, Z direction. So that is called chaotic, vigorous, turbulent mixing, right? Next one is this is the laminar mixing. So mixing is happening layer by layer due to the presence of shear stress. You see how smoothly this is mixing. There is no vigorous, irregular patterns. Next one is the comparison between turbulent and laminar mixing. This is the turbulent regime, this is the laminar regime. So you can clearly see the difference, how vigorously turbulent one is mixing and how layer by layer with a particular pattern laminar mixing is happening. Right? Next one is the molecular diffusion. So it is happening at the molecular level in which molecules diffuse due to the thermal motion. So due to the thermal motion, it is creating this mixture at molecular level, right? Next question. In agitator, the fluid's depth is controlled approximately equal to the diameter of the vessel. Is it true or false? In agitator, the fluid's depth is controlled approximately equal to the diameter. The answer is true. In agitator, the depth of the fluids and the diameter of the vessel is kept same. Next, what are the different types of impellers? What are the different types of impellers? The impellers are used for create flow patterns, right? So what are their types? So what are the different types of impellers? There are three types: propellers, turbines, and paddles. So under this division also there are subdivisions like free bed turbine mixer, open straight blade turbine mixer, next bladed disc turbine, This is the most of the turbines part. Vertical curved blade turbine. Last one is the pitched blade turbine. Okay. Next, different types of flow patterns. What are the different types of flow patterns? So mostly two types of flow patterns are seen, right? Vortex and swirling. So you can see that different kinds of vortex are created through this impeller, right? So this is the swirling one. Swirling perpetuates stratification at the various levels without accomplishing longitudinal flow between levels. Swirling pattern develops if a low viscous fluid is started in an unbaffled vessel by a centrally mounted impeller. So this is swirling. Next, the formation of vortex and swirling reduce the dash. Fill in the blanks. The formation of vortex and swirling reduce the degree of agitation and mixing. Okay. Next, in which type of fluid propeller is used? In which type of fluid propeller is used? The viscosity of the liquid should be less than 50 poise. Okay. So more than that, if the fluid viscosity is more than 50 poise, propellers cannot be used, like in case of castor oil or glycerol. Okay. Next, turbines rotate at a lower speed than the propellers. Is it true or false? Turbines rotate at a lower speed than propellers. Is it true or false? The answer is true. Turbine rotate at lower speed than the propeller. Next, what are the three velocity components of impellers? What are the three velocity components of impellers? The first one is the radial velocity component. Second one is the longitudinal velocity component. And third one is the tangential or rotational velocity component. So radial velocity component acts in the direction of perpendicular to the shaft of impeller. Longitudinal in the parallel direction, parallel with the shaft. And tangential rotational acts in the direction of tangent to a circular path around the shaft. Okay. Next. Okay. So this is it. Next. What is the relation between volumetric flow rate and with impeller diameter? What is the relation between volumetric flow rate with the impeller diameter? So volumetric flow rate is proportional to that impeller diameter cube, right? So this is the expression, right? Then Q is the flow number, N is the rotation of the impeller, rotation of the impeller, and dA is the impeller diameter. Next, flow number is constant for all type of impellers. Flow number is constant for all type of impellers. Is it true or false? The answer is false. So for different impellers, flow number is constant. Okay. No, I think flow number is constant for all type of impellers is true. Yes, this is true. My mistake. So flow number is constant for all type of impellers is true. Next, what is the value of flow number in marine propellers? What is the value of flow number in marine propellers? The answer is 0.5 for marine propellers. So 1.3 is for flat blade turbine. This is for marine propellers. 0.87 is for 4-blade 45-degree turbine, right? Yes. Next, what is the relation between power consumption with the impeller diameter? The answer is E. So power consumption is proportional to diameter to the power 5. That is P equals to NP rho N cube dA to the power 5. NP is the power number, rho is the density of the fluid, N is the rotation you know, and dA is the impeller diameter. Next, for flow low Reynolds number, the power number is inversely proportional to Reynolds number. Is it true or false? For low Reynolds number, the power number is inversely proportional to Reynolds number. Is it true or false? So the answer is true. For low Reynolds number, power number NP is inversely proportional to Reynolds number. Next, for higher Reynolds number, the power number is what? For higher Reynolds number, the power number is independent of Reynolds number. Okay? Independent of Reynolds number. Next, what is the expression of mixing time in a vessel? What is the expression of mixing time in a vessel? So mixing time can be predicted by this correlation where V is the volume of the vessel. Okay, so it is pi dt square h by 4. Dt is the diameter of the vessel and h is the height of the vessel into 1 by q. Q is the velocity, flow rate, volumetric flow rate. So what is it? 0.92, that is flow number is 0.92 in dA cube dt by dA. Okay. So now how can we calculate it? So this is the flow number expression. If we simplify this, it will come N T dA by dt whole square, right? Into dt by h equals to 4.3 is a constant. It is a constant. Okay, this is the expression of mixing time in vessel. Next, what is draft tube? What is draft tube? So, it is a tube which is mounted around the impeller or mounted immediately above the turbine. Okay, this is the draft tube. So why it is used? When the direction and velocity of flow to the suction of the impeller are to be controlled, draft tubes are used. Okay. So now I will do some numericals. Okay. So let's start. So first one is an agitated baffle vessel is being used to prepare uniform solution of viscosity to centipoise. Running the agitator at 100 rpm so as to obtain a Reynolds number of 50,000. If the content of the vessel are replaced by solution of viscosity 4 centipoise and agitator rpm is increased to 200, how much will the power requirement change? So RE is said 50,000. That means RE is greater than 10 to the power 4, that is turbulent flow. So in case of turbulent flow, power number is independent of the Reynolds number, right? So power number or power consumption is proportional to, power consumption is Np rho n cube dA to the power 5. So P is proportional to rotational speed cube. So P1 by P2 equals to N1 cube by N2 cube, right? So N1 cube is 100 cube and N2 is 200, right? So P2 will be, it is nothing but 1 by 2 cube, that is 1 by 8. So P2 will be 8 P1. So that means how much percentage change is there? So percentage change is, final pressure is 8 P1, initial pressure was P1 divided by P1 into 100%, that is 700% power requirement change is there. This is answer. Okay. Next, we will do two more problems. Next, uh, so second one, a small model reactor is to be built for scale up studies of the behavior of purpose large industrial mixing tank reactor having 1000 times capacity. The bigger unit of 2-meter diameter will have a liquid depth of 2 meters. This will be fitted with 4 bladed turbine of 0.6 meter diameter. Now first problem. Estimate the dimension of smaller unit. And second one, for the optimum mixing speed of 330 RPM observed in the smaller model. What will be the recommended speed in the industrial unit under the following conditions? So what are the conditions? A is power per unit volume is kept constant. And second one is Reynolds number does not change. Okay. So the answers are so for both of the unit, L by D equals to 1, right? Because 2 meter is the diameter and 2 meter is the liquid depth. So it is 1 for the bigger one as well as the smaller one, right? And volume of the bigger one is 1000 times of the smaller one, it is said. So now we can calculate it, right? So what is the volume of the bigger one? Pi by 4 d square h. So pi by 4 d is also 2 meter, h is also 2 meter. So it is coming as 6.28 meter cube, right? Now smaller one will be V2 by 1000, right? So V1 is 6.28 into 10 to the power minus 3 meter cube. Now similarly we can calculate the smaller diameter. So pi by V1 is pi by 4, smaller diameter and smaller tank diameter, smaller tank height equals to 6.28 into 10 to the power minus 3. So we already know that h by d is same, right? H and L are here is the same thing. Okay. So here also L by D ratio is same. So it will be nothing but pi by 4 ds cube equals to 6.28 into 10 to the power minus 3. So from here we can calculate ds, the smaller diameter of the vessel. So how much is it coming? So it is coming at 1. It is coming at 0.2 meter. This is the smaller tank diameter is 0.2 meter. Okay. Now we need to know the impeller diameter or turbine diameter, right? So how will you calculate? So this is the bigger vessel, this is the smaller vessel, right? So this is 2, this is also 2. So here also this is 0.2, this is 0.2. So from similarity, we considered that the bigger vessel diameter is 2 divided by smaller vessel diameter equals to bigger vessel turbine diameter divided by smaller vessel turbine diameter. That is, so now from similarity dt can be calculated to 0.06 meter. Okay, this is the model. So first question 1 is answered. Question 1 is asked, estimate the dimension of the smaller unit. For 2, it is asked to calculate the rotational speed for the following 2 cases. Right? So the first case 1 was the power per unit volume is constant. Okay? This is the case. So in case of turbulent flow, we know that P is power consumption is power number rho n cube dA to the power 5. Right? So power per volume is Np rho n cube dA to the power 5 divided by V. V is nothing but the volume of the tank. So Np rho n cube dA to the power 5 divided by pi by 4 dA square into L, right? Or you can write P by V equals to Np rho n cube dA to the power 5 divided by pi by 4 dA cube, because in this case dA equals to L, right? So what is coming? It is coming as P by V Np 4 Np rho n cube dA square divided by pi. So P by V is proportional to n cube dA square, right? So this is constant. That means n1 cube dA1 square equals to n2 cube dA2 square. So n1 is, suppose n1 is the bigger tank. So this needs to be calculated. So n1 cube, its turbine diameter is 0.6 square equals to N2, 330 cube into 0.06 whole square. So what is N1? This is 71.09 RPM. This is the answer for the case 1. Now for the case 2. Now for the case 2. Now for the case 2, it is asked that the Reynolds number is constant, right? So Reynolds number is constant. So what is the expressions of Reynolds number? N dA square rho by mu, right? So for both case it is constant, means N1 dA1 square rho by mu, N2 dA2 square rho by mu. So rho by mu is same for the fluid because same fluids are used. So N1 dA square, so N1 dA is again 0.6 squares, N2 is 330 into 0.06 whole square. So N1 is coming as 3.3 RPM. This is the rotational speed for both the cases. Okay. Next question. This is a very simple question. A batch bioreactor is to be scaled up from 10 to 10,000 liters. The diameter of the large bioreactor is 10 times that of the small bioreactor. The agitator speed in the small bioreactor is 450 RPM. Determine the agitator speed of the large one with same impeller tip speed as that of small bioreactor. So for same impeller tip speed means NDA equals to constant. Okay, so N1 equals to DA1 equals to N2 into DA2. N1 is the large one, so DA1 diameter is 10 times of the smaller one, right? And N2 is given as 450 RPM and diameter is DA2. So N1 will be the large one, rotational speed, that will be 450 by DA2. DA2 will be cancelled out into 1 by 10 is nothing but 45 RPM. So this is the answer. Right? So I think these problems will be helpful, and this question answer what I have discussed in the class will be helpful to solve these week's assignments. We'll meet on next Saturday. Till then, goodbye.